We're already familiar with the chi-squared statistic. If you're not, I encourage you to review the videos on that. And we've already done some hypothesis testing with the chi-squared statistic. And we've even done some hypothesis testing based on two-way tables. And now we're going to extend that by thinking about a chi-squared test for association between two variables. So let's say that we suspect that someone's foot length is related to their hand length, that these things are not independent. Well, what we can do is set up a hypothesis test. And remember, the null hypothesis in a hypothesis test is to always assume no news. So what we could say is here is that there's no association between foot and hand length. Another way to think about it is that they are independent. And oftentimes what we're doing is called a chi-squared test for independence. And then our alternative hypothesis would be our suspicion. There is an association. There is an association. So foot and hand length are not independent. So what we can then do is go to a population and we can randomly sample it. And so let's say we randomly sample 100 folks. And for all of those 100 folks, we figure out whether their right hand is longer, their left hand is longer, or both hands are the same. And we also do that for the feet, and we tabulate all of the data. And this is the data that we actually get. Now, it's worth thinking about this for a second on how what we just did is different from a chi-squared test for homogeneity. In a chi-squared test for homogeneity, we sample from two different populations, or we look at two different groups, and we see whether the distribution of a certain variable amongst those two different groups is the same. Here, we are just sampling from one group, but we're thinking about two different variables for that one group. We're thinking about feet length, and we're thinking about hand length. And so you can see here that 11 folks had both their right hand longer and their right foot longer. 3 folks had their right hand longer, but their left foot was longer. And then 8 folks had their right hand longer, but both feet were the same. Likewise, we had 9 people where their left foot and hand was longer, but you had 2 people where the left hand was longer, but the right foot was longer. And we could go through all of these. But to do our chi-squared test, we would have said what would be the expected value of each of these data points if we assumed that the null hypothesis was true, that there was no association between foot and hand length. So to help us do that, I'm going to make a total of our columns here and also a total of our rows here. Let me draw a line here so we know where this is going on. And so what are the total number of people who had a longer right hand? Well, it's going to be 11 plus 3 plus 8, which is 22. The total number of people who had a longer left hand is 2 plus 9 plus 14, which is 25. And then the total number of people whose hands had the same length, 12 plus 13 plus 28, 25 plus 28, that is 53. And then if I were to total this column, 22 plus 25 is 47 plus 53, we get 100 right over here. And then if we total the number of people who had a longer right foot, 11 plus 2 plus 12, that's 13 plus 12, that is 25. Longer left foot, 3 plus 9 plus 13, that's also 25. And then we could either add these up and we would get 50, or we could say, hey, 25 plus what is 100? Well, that is going to be equal to 50. Now, to figure out these expected values, remember, we're going to figure out the expected values assuming that the null hypothesis is true, assuming that these distributions are independent, that feet length and hand length are independent variables. Well, if they are independent, which we are assuming, then our best estimate is that 22% have a longer right hand, and our best estimate is that 25% have a longer right foot. And so out of 100, you would expect 0.22 times 0.25 times 100 to have a longer right hand and foot. I'm just multiplying the probabilities, which you would do if these were independent variables. And so 0.22 times 0.25 let's see, 1/4 of 22 is 5.5. So this is going to be equal to 5.5. Now, what number would you expect to have a longer right hand but a longer left foot? So that would be 0.22 times 0.25 times 100. Well, we already calculated what that would be. That would be 5.5. And then to figure out the expected number that it would have a longer right hand, but both feet would be the same length, we could multiply 22 out of 100 times 50 out of 100 times 100, which is going to be half of 22, which is equal to 11. And we can keep going. This value right over here would be 0.25 times 0.25 times 100. 25 times 25 is 625, so that would be 6.25. This value right over here would be 0.25 times 0.25 times 100, which is again 6.25. And then this value right over here, a couple of ways we can get it. We can multiply 0.25 times 50 times 100, which would get us to 12.5. Or we could have said this plus this plus this has to equal 25, so this would be 12.5. And now this expected value we can figure out because 5.5 plus 6.25 plus this is going to equal 25. So let's see, 5.5 plus 6.25 is 11.75. 11.75 plus 13.25 is equal to 25. Same thing over here. This would be 13.25 because this is 11.75 plus 13.25 is equal to 25. If we add these two together, we get 26.5. 26.5 plus what is equal to 53? Would be equal to another 26.5. Now, once you figure out all of your expected values, that's a good time to test your conditions. The first condition is that you took a random sample, so let's assume we had done that. The second condition is that your expected value for any of the data points has to be at least equal to 5. And we can see that all of our expected values are at least equal to 5. The actual data points we got do not have to be equal to 5. So it's okay that we got a 2 here because the expected value here is 5 or larger. And then the last condition is the independence condition, that either we are sampling with replacement or that we have to feel comfortable that our sample size is no more than 10% of the population. So let's assume that that happened as well. So assuming we met all of those conditions, we are ready to calculate our chi-squared statistic. And so what we're going to do is for every data point, we're going to find the difference between the data point 11 minus the expected, minus 5.5, squared over the expected. So I did that one. Now I'll do this one. So plus 3 minus 5.5 squared over 5.5 plus, now I'll do this one, 8 minus 11 squared over 11. Then I'll do this one, 2 minus 6.25 squared over 6.25. And I'll keep doing it. I'm going to do it for all 9 of these data points. And I actually calculated this ahead of time to save some time. And so if you do this for all 9 of the data points, you're going to get a chi-square statistic of 11.942. Now, before we calculate the p-value, we're going to have to think about what are our degrees of freedom. Now, we have a 3 by 3 table here. So one way to think about it, it's the number of rows minus 1 times the number of columns minus 1. And this is 2 times 2, which is equal to 4. Another way to think about it is if you know 4 of these data points and you know the totals, then you could figure out the other 5 data points. And so now we are ready to calculate a p-value. And you could do that using a calculator, and you could do that using a chi-squared table. But let's say we did it using a calculator, and we get a p-value of 0.018. And just to remind ourselves what this is the probability of getting a chi-squared statistic at least this large or larger. And so next, we do what we always do with hypothesis testing. We compare this to our significance level. And we actually should have set our significance level from the beginning. So let's just assume that when we set up our hypotheses here, we also said that we want a significance level of 0.05. You really should do this before you calculate all of this. But then you compare your p-value to your significance level, and we see that this p-value is a good bit less than our significance level. And so one way to think about it is, we got all these expected values assuming that the null hypothesis was true. But the probability of getting a result this extreme or more extreme is less than 2%, which is lower than our significance level. And so this will lead us to reject our null hypothesis, and it suggests to us that there is an association between hand length and foot length.